So, in the last module, we stopped with the idea of thermally fully developed condition, and we had to write the non-dimensional temperature distribution. So, that theta is given by T wall, which is a function of x, minus T local, which is a function of r comma x, divided by T wall, which is a function of x, minus T bulk mean, which is a function of x. This theta is what we are going to use. Please remember, this slide which I showed in the last module was distinguishing between the velocity and the heat transfer aspect. What changes, what does not change. Okay. Here velocities are all going to remain constant, maximum, mean, etc. Here none of the temperatures which we are talking about, local bulk mean temperature, local wall temperature, nothing is going to remain constant, because heat is being added or removed. In external versus internal flow, this is something which, see, because we are forced to teach fluid mechanics and heat transfer at different semesters, students tend to compartmentalize fluid mechanics as a separate entity, heat transfer as a separate entity. While that may be true for conduction heat transfer, convection heat transfer needs to keep, it is like the two wheels of a cart, you know. One wheel is fluid mechanics, which is causing the bulk transport. So, I have to have the fluid mechanics part completely linked with the heat transfer part. So, I cannot escape from going back to fluid mechanics at every little instant. So, here again I will draw an analogy between external flow in fluid mechanics and the heat transfer aspects of external flow. External flow, this is in external flow we would have seen this, but I am just bringing this to your notice again. You have u infinity, t infinity, you have u and t. So, t wall was there, u infinity, this is local u, this is local t. I was dealing with u local x comma y, u infinity, which is a constant, t local x comma y, t wall and t infinity. Okay. In internal flows, now again, now that we have seen internal flows, in internal flows what are the things I deal with? U of r comma x instead of x comma y, that really does not matter. U bulk mean, which takes the role of u infinity. U infinity was the velocity with which the fluid came in. Once the fluid comes in into this confined channel, confined boundary, u infinity loses its significance completely. You are dealing with u bulk mean. Okay. That is like one kind of an average velocity, or you can at best deal with u center line or something like that. Here t of r comma x, t wall local, t bulk mean local, t infinity which was there before is long useless now. U infinity and t infinity are kind of not useful anymore after the fluid has come into the pipe. So, if you go back and compare local quantities u infinity and t infinity. So, at best the velocity can vary from 0 to u infinity, temperature can vary from T wall to T infinity, correct. So, here what we are saying is u infinity does not have any address, any value. You are going to be concerned with a velocity distribution, you are going to be concerned with a temperature distribution, and the bulk mean quantity is what is going to be repeatedly used as some kind of a separator between, or how to relate a local quantity to some average quantity. Here we related it to the maximum quantity, now here we are going to relate it to the average quantity. This is something which you should communicate effectively to the student. Okay. Now, if we take a look at this thermally fully developed condition, see, I have drawn this diagram was drawn with T wall greater than T bulk mean. Okay. This same thing can be drawn for T wall less than T bulk mean. So, if my fluid is going to get cooled, my temperature profile would be this. Okay. Thicker here, T wall at x1, T wall at x2 would be smaller, T wall at x2 smaller than T wall at x1, meaning Q is going out of control volume, heat is leaving the control volume. Similarly, T bulk mean at x2 is going to be less than T bulk mean at x1, T local r comma x2 is going to be lower than T local r comma x1. Okay. We do this for heat flowing into the control volume. So, this is T wall greater than T bulk mean, heating of fluid. This is cooling of fluid, but conceptually nothing is going to change. So, we will do the analysis for this case, keeping in mind that the same analysis is valid for cooling also. So, let us define a non-dimensional theta like this, and the concept of thermally fully developed is that the derivative of this quantity d theta with respect to x is equal to 0. This one. What was the definition of hydrodynamically fully developed? This is thermally fully developed. Hydrodynamically fully developed, it is always good idea to compare this notes again and again. Du by dx is equal to 0, hydrodynamically fully developed. So, we are not saying any of these temperatures are not going to vary with respect to mathematically. This is d by dx of something is 0, means that particular something is not changing in the x direction. What is that particular something here? Here it is velocity, local velocity. Here it is a non-dimensional temperature, which is a combination of bulk mean, wall and local. So, though each of these quantities T wall, T bulk mean and T local, T wall is changing, T local is changing, therefore, T bulk mean is changing. Even though all these three quantities are changing, the change is not arbitrary. The change is going to happen in such a way that this condition is going to be satisfied for the fluid to for the flow to be thermally fully developed. This is a very, very important concept that you need to bring it to the attention of the students, make them understand the thermally fully developed condition does exist in real life, and it is a very important significant simplification that can happen, and we are going to see that very quickly. So, if d theta by dx is equal to 0, that means this non-dimensional quantity is independent of x. Derivative of something is 0 means it is constant with respect to x. So, it is independent of x. That means this quantity derivative with respect to r must be also independent of x. So, I can write d theta by dr, which is d by dr of T wall minus T local, this one. I am dropping this subscript, this bracket x everywhere, okay, because that is understood. This evaluated, let us evaluate at r equal to capital R. Why do we want to do that? That we will see in a minute. This one Tm Tw, look, let us look here. Tm Tw are only functions of x. So, it will come out when I am differentiating with respect to r. This is also going to be only a function of x. This Tw also when you differentiate, it is going to come out. So, what I am going to get is 1 over T wall minus T bulk mean, which is only a function of x. Derivative of T wall with respect to r is 0. Derivative of this quantity is nothing but minus d by dr of T local, which is not equal to a function of x. Why? Because this quantity by itself was not a function of x. So, its derivative with respect to r is also not a function of x. What is minus dt by dr evaluated at r equal to capital R? What is that quantity? So, remember our definition of heat transfer coefficient. So, what is the definition of heat transfer coefficient? H minus k dt by dr evaluated at r equal to r divided by some temperature difference. This quantity is your heat transfer coefficient. So, why this becomes plus? Because of the same logic we had in fluid mechanics, r is going this way, y is going this way, minus k dt by dy at y equal to 0 is equal to saying k dt by dr at r equal to capital R. Why? Because y is equal to capital R minus small r, y is increasing this way, r is decreasing this way. So, using this transformation, dy is minus dr. So, I substitute for this as minus dr, I will get plus k dt by dr evaluated at r equal to capital R. So, this H is what we have in fact carried here. This quantity which I derived here is nothing but my heat transfer coefficient, and this heat transfer coefficient is not going to be a function of x. A very useful and important result. What does it mean? In thermally fully developed region, so in thermally fully developed region, heat transfer coefficient, local heat transfer coefficient is constant. How do I know that? H local, which is nothing but k dt by dr evaluated at r, T wall minus T bulk mean, is not a function of x. This means heat transfer coefficient after the boundary layers have merged is constant. A very useful result. Remember, in hydrodynamics, what did we say? Friction factor was constant after hydrodynamically fully developed region was achieved. What are we saying now? Heat transfer coefficient is constant. So, I hope the connect is seen very clearly. Variation of velocity with respect to y is directly related to friction factor. Variation of temperature with respect to y or r is directly related to the heat transfer coefficient. The behavior of the heat transfer coefficient is exactly like how the friction factor is going to behave. So, if I were to use the same logic, let us write that friction factor is equal to constant after LH and beyond. Hydrodynamic entrance length, heat transfer coefficient is constant at L, what do you call this, thermal entrance length LT and beyond. Okay. Please remember now, there are a couple of expressions which you can write. Laminar flow hydrodynamic entrance length is approximately given by 0.05 Re times d. Thermal entrance length for laminar flow through pipes is given by 0.05 Re times Pr times d, or it is nothing but Pr times L hydrodynamic for laminar flow. Okay. Now, how are these two related? For again, I will keep going back to external flow because that is something which we have already seen. External flow, flat plate, delta T. Please remember, this is highly exaggerated. We would have seen what are the typical dimensions of the boundary layer thicknesses. Boundary layer thicknesses are of the order of a few millimeters. Okay, so I am just drawing this exaggerated. Velocity boundary layer is still delta, so I am going to have profile which is going to be constant after that. Thermal boundary layer is till delta T, the profile is going to change after that until this location. So, u infinity, T infinity, u of x comma y, T of x comma y, this is still u infinity. Okay. We have seen how the regions are going to get separated, and what is this case? This is the case where delta T is greater than delta. What does it mean? Prandtl number is less than 1. So, you are seeing, right. So, the delta T is going to grow at a faster rate. What does it mean? The fluid is transporting heat at a faster rate than it is able to transport momentum. Now, when I go to internal flows, I can have these 3 cases coming to me different interpretations. So, if Prandtl number is equal to 1, approximately equal to 1, delta grows at the same rate as delta T. What does this mean? The hydrodynamic entrance length and the thermal entrance length. The green one is hydrodynamics, the purple one, or let me use the black one here, the black one is the heat transfer or thermal boundary layer. This is the delta T, the green one is the delta. Both of them are growing at the same rate. So, L hydrodynamics is almost equal to L thermal. In this case, it is virtually the same. Prandtl number is approximately equal to 1. What does this mean? This means that the location where the flow is hydrodynamically fully developed is same as the location where the flow is thermally fully developed. So, beyond this point, velocity, so it's, please imagine this as 2 pictures being superimposed on each other. The velocity profile, the carrier of the heat is not going to vary with respect to axial location. The temperature profile is also going to change, but the change is going to be governed by this law, that is theta, d theta by dx is equal to 0 at beyond this point, and the point where this 2 is happening is exactly the same. Very nice, it makes life easy. As we saw here, my energy equation, when I try to solve, rho Cp u dt by dx, the u here is now going to be invariant at any x, just as how u became equal to u infinity in this part. When I looked at the Navier-Stokes equation beyond y equal to delta, I had to use u when I had the coupling rho Cp u dt by dx. The u was a constant u infinity instead of a variable u which was used here. So, the splitting of the region of the flow field into 3 parts, 0 to delta, delta to delta t and beyond, was made possible, and simplifications were possible because of this idea of Prandtl number. Now, if I have Prandtl number greater than 1, that means Prandtl number greater than 1, delta grows at a faster rate as compared to delta t, which means I take this pipe, delta grows faster. So, delta is this, thermal boundary layer is slow, is thinner, right. This purple is delta t, the black is delta. The hydrodynamic entrance length was here, the thermal entrance length is here. Hydrodynamic entrance length was here. So, Prandtl number greater than 1, delta greater than delta t, L hydrodynamic less than L thermal. What does it mean? This is from just the diagram we are able to say, but more importantly what it means is that even after the location of where the velocity has become fully developed, the temperature is not able to become fully developed. Only beyond this point. So, I can, if I split the flow region into 0 to x less than LH, LH less than or equal to x less than or equal to LT, x greater than or equal to LT, 3 regions. Here both U and T vary, only T varies, and here fully developed. Okay. So, T varies, of course, here also what I mean by vary is, I will write U and T developing. Here T is developing, U has become fully developed. This will result in different simplification of the energy equation. Now, consider the case for Prandtl number less than 1, delta less than delta T. We draw the same thing here. A pipe is drawn. Delta grows at a slower rate, so it is going this way, whereas delta T grows very fast. Sorry about that, this is delta T. So, delta T is here, thermal entrance length is here, whereas the hydrodynamic entrance length is this one, LH. PR less than 1, this is delta, this is delta T, delta is thinner than delta T, LH is greater than LT, LH is greater than LT, and if I have to split the region, I have to split it as 0 less than or equal to H less than or equal to LT, LT less than or equal to H less than or equal to LH, X greater than or equal to LH, fully developed both hydrodynamically and thermally. This is thermally fully developed, hydrodynamically developing, here, and this both U and T developing. I hope you are able to appreciate the difference here. Therefore, when I am in this part, in the middle part, in this region, my temperature profile has now reached the fixed shape. It is just going to expand like that. Velocity is of course changing with respect to x direction. When I am in this part, du by dx, wherever du by dx is occurring in the equation, that will all go to 0. So, my equations become very, very simple, or simplified equations are there. Next, we are going to do what we call as the energy balance, simple, effective, useful all through. Every student at the end of an undergraduate heat transfer course should be able to do this, meaning there are certain non-negotiable aspects that one needs to tell the student. Look, if this is the course that you are doing, this much you have to know: fluid mechanics, definition of Reynolds number, friction factor, head loss due to friction. These are terms and concepts that he or she has to remember and be able to apply. Energy balance is one such concept which the student needs to be able to appreciate, understand and apply for any problem, however complex it may be. Okay. So, what is it? Consider a flow through a pipe here, subject to constant wall heat flux condition. This is being done for this case. It will also be done for the case of constant wall temperature. Why are we studying these two cases? In real life, we would have situations where the temperature as well as heat flux may not be constant, but to do analysis for such kind of geometries, such kind of situations may become quite mathematically unwieldy. So, many times, like for example, if you take a nuclear fuel rod, okay, this is a nuclear fuel rod, length is of the order of 3.6 or 3 meters, diameter is of the order of 12 millimeter. This contains fuel elements or fuel pellets, like like this, cylindrical bullet like structures which are fitted here, which are filled into a pipe, and this is your fuel rod. the pipe is not, the fuel rod is not generating uniform heat. It is generating power which is going to vary sinusoidally, typically like this. How this is obtained? This is obtained by giving various pellets of different enrichments, so on and so forth, so that I get a profile like this. Now, this profile can be given a mathematical form q naught sin pi z by h or something, where this is your capital H. Okay. But in real life, this is a mathematical fit to something which is like this: constant, another constant, another constant, constant, constant. So, in real life situation, you cannot get smooth functional variation in temperature. You will mathematically transform these things into but through an equation to a smooth function. So, for example, if I am going to do the analysis of this part, I can do it as this region has a constant heat flux given by Q1 double prime. This one has a constant heat flux Q2 double prime. This is Q3 double prime. This is again Q2 double prime, Q1 double prime. I can do the analysis this way or do the sinusoidal function and do the analysis. Whatever be it, in engineering, most applications would either be having or can be converted to heat wall temperature constant or heat flux constant situations. So, that is why these two situations are widely studied in engineering. In the next module, we will go through the energy balance for flow through a pipe, circular pipe, subjected to constant wall heat flux condition. We will list down the assumptions, derive expressions for the bulk mean temperature of the fluid and the wall temperature, and therefore get the value of the heat transfer coefficient. Thank you.